Okay, so let us start from where we stopped. We had this the solution for the single agent where it is like a posted pricing. So, if you recall, we were trying to optimize the revenues, maximize the revenue subject to the condition that it is both BIC and also individually rational, and we are just trying it for one agent, and it turned out that for one agent the optimal solution is to set a specific price, give the item to that agent if its value is above that price, or not to sell after if that is not the case. Now, let us try to generalize the same idea for more than one agent, n agents in general. So, now no longer the BIC, DSIC are no longer equivalent, IIR and all those things, we will have to look at each of them separately. So, the mechanism is optimal, that is revenue optimal, if it maximizes the revenue subject to the BIC and IIR condition. That is our objective. Because it is BIC and IIR, we have to satisfy that FIs, this the allocation probabilities have to be non-decreasing in expectation. That is good enough because we do not need non-decreasingness. So, that weaker example that we saw, some of the blocks were 1, some of the blocks were blank, that kind of a structure is fine. And of course, we can also have non-decreasingness, but that is more than what we need. And this pi I Ti, so this is the expected payment when agent i's type is Ti, that has a specific integral formula, and that constant of the integration should be 0 because that is a requirement. The IIR requirement is it cannot be non-negative, non-positive, and we are just setting it to the highest possible value. Okay. And our objective is that expected payment made by this agent I. So, now let us look at the same quantity. So, this was the same for the previous case as well. If I look at how much expected revenue we earn from this player I, that is given by how much payment that it makes and what is the distribution of that type of that player, right. So, this is just the revenue earned from that agent, and which can actually be simplified in a very similar way. We do not want to redo this. So, WITI do the same calculation, that will be this virtual valuation of agent I. Now, the only difference is that G also has a subscript, that the distribution for different agents could be different. Somebody may have a uniform distribution, somebody may have a Gaussian, not Gaussian, maybe some other type of distribution, exponential distribution. Yeah, so all these things are captured in this small gi and the capital GI, and accordingly the virtual valuations could be different. These Wi functions could be different for different agents, and alpha I Ti as before we have defined. So, the expected payment given by this agent I, you can actually, okay, so what one can do is you can multiply. So, this Ti I can just add everyone's type. So, even though you can think of this integral over Ti and then integrating over T minus I, I am just writing that in a compressed way, because that gives rise to this GT, which we will use later on just for a convenience. This is just for the other agents, it is getting marginalized anyway. Now, our objective is to maximize the sum generated by the sum of the payments of all the agents, right. So, this is, if you just call it the payment of agent I, I am just summing it over all the agents. So, some of the agents will win that object depending on what Fi you have chosen, some of them will not win that object, but we are just taking the sum of all of them. And so, yeah, so you can, so there is no problem here, you can actually put that summation inside and then do this integration. So, what we really want to see is, so this is independent of any agent I, but these two things are dependent on agent I. So, we want to see what is happening in this particular case, right. So, as before, if we, and the only restriction that we have so far is this, each of these FITs has to be monotone, because that is the requirement for the BIC. So, in fact, FIT does not necessarily need to be monotone, all that you need is this alpha I to be monotone. But yeah, so some condition needs to be satisfied for F. So, currently we are not looking at that, we are just trying to maximize this quantity. So, how should we actually maximize this? If there is no other constraint, how should we actually maximize this? It is very similar to the single agent problem. So, I have n different agents, let us say 3 different agents, they have W1, W2, W3, and at some specific t I will have to decide what whom I should give the item to, or in what with what probability I should give this item to which agent. This is the same as it has similarities with what we did for the sponsor search slot allocation problem, right. You have, so remember that for every t the sum of Fi has to be less than or equal to 1, right. You cannot allocate the item, I mean the sum of the probabilities cannot be more than 1, have to give it to someone, or so think of this sum as some masses that you are going to put on all these weights. So, these weights are already fixed, you have calculated that weight, and you are trying to maximize this. So, which is that Fi, how should you distribute it such that the sum is maximized?
Assign largest value to such a I, so that Wi is maximum for that.
Exactly. So, you want to maximize, so whoever has the highest virtual valuation at that type profile, you will, so you will put entire mass 1. If there are ties, then you can split it in any way you want, but that will give you the same revenue or same weighted sum here. So, okay, so that is the starting point. Let us say this is our proposal. What might go wrong here? Will that allocation policy be monotone? Because that is something that we need to be careful about. So, let us do that and let us see where is this where we hit. So, the maximization problem is still the same, subject to the condition that F is non decreasing in expectation, that is our complete optimal maximizing the revenue problem. Now, as we said that the unconstrained optimization problem looks like that I can give it to the agent who has, so whenever I see somebody at that type profile, so is at this type profile, I look at everyone's virtual valuation, whoever has the highest virtual valuation, you sell it to that agent. Otherwise, you give, so otherwise that agent is not allocated, and of course, we do not want to gain any negative revenue. So, if it turns out that for all agents the virtual valuations are negative, then I will not sell the item, right. This sounds plausible until the point that suppose this again comes to this virtual valuation. If this virtual valuation had this up and down kind of a structure, right. So, then it may so happen that in some profile, let us say t minus i's are fixed. So, I happens to be the virtual value maximizer at some point at some ti, but at ti prime which is larger than ti, you had a dip, this wi actually reduced. So, then that does not maintain this maximum point. So, you allocate the item to somebody else. So, then that violates the condition that it is monotone, right. So, as before we will have to, so I mean the counter example is not difficult to create. So, you can create a counter example where if the virtual valuation is not monotone, the virtual valuations wi is not monotone with respect to ti, then you will not have the unconstrained optimization problem will not give you the optimal mechanism. So, what we do, we actually use the same regularity assumption, right. So, we are going to assume that the virtual valuation is regular. So, this is the term that Meyerson used and therefore, everybody else used. The virtual valuation wi is regular if you have this monotonicity property with Wi, and of course, the exponential class of distributions and also the uniform distribution, all of them satisfy actually a stronger condition called the monotone hazard rate. So, therefore, they also satisfy this regularity condition. So, for those type of classes of distribution, we can always say that okay. So, this is, if you solve this unconstrained problem, you are doing the right thing, you are going to give the item to the one who maximizes the virtual valuation, right. So, that is essentially the whole idea. I mean it just a small change from the previous setup to this setup. Now, there is no price anymore. So, it is not a posted price, because when you had only one agent, the point there was no other agent. You are only deciding whether this virtual valuation is positive or negative. If it is positive, you give it. If it is negative, you do not sell it. And the point at which you will sell, or the payment that you will make, is exactly the point where the virtual valuation attains that value of 0. Now, that is not sufficient here, because you of course want at least one agent to have positive virtual valuation, otherwise you will not sell the item, but it is dependent on others' valuations as well, right. So, the payment that you will make under this mechanism, just like any auction where there are more than one agent, it will be dependent not only on your type, it will be also dependent on what the types of the others are. If their valuations are very high and therefore, their virtual valuation is also high, you will not win the object, and if you happen to win the object, you will have to so apply that payment formula, and then you will get that at what point. So, what is the payment that should be made. So, this is only the allocation part. So, if everyone's valuations are regular, is the same of the solution of the unconstrained problem. So, yeah, so we are not going to prove that from scratch, because we have already proved it. So the argument that we just said. So, what we observe now is that the allocation is actually monotone, and therefore, it is not only just non-decreasing in expectation, it is actually non-decreasing. It is giving me more than what I wanted. So, I assume that this WITI is monotone non-decreasing, and I allocated the item to the agent who has the maximum virtual valuation. That means that if I look at the Fi of Ti minus I, that also is monotone non-decreasing with respect to Ti. It is monotone non-decreasing, not just non-decreasing in expectation. So, we wanted to have a BIC mechanism, we got a DSIC mechanism as an optimal mechanism. Okay, so, that is it. So, the optimal mechanism design problem, this solution, if the Wi's are regular, then that the allocation problem is this. You give the item to the agent who has the highest virtual valuation. It is deterministic, as you can see, you give it completely. So, it started with maximizing the revenue with respect to any randomized mechanism, but what we finally got is a deterministic mechanism. Either I will not sell it, or I will sell it to exactly one agent. So, yeah, so our objective was on this larger space, we wanted BIC IIR randomized mechanism, and sitting inside this class, a small, possibly small class of mechanisms which are DSIC, individual irrational, and deterministic. The optimal mechanism actually sits inside that. Okay, so now let us finish this exercise with the payment part as well. So, the payment, even though it is written in a little in order to make it more mathematically correct, it has become a little more clumsy, but the way you should interpret this as, so there exists some, so W inverse of 0 means that the point at which agent i's virtual valuation starts becoming positive. This Wi is a monotone function, so when you invert the 0 point, you get the point like this one. Okay. So, beyond which you will be, so we will definitely sell it after it crosses that line, and it also should be the point where the second highest valuation is beaten, right. So, you will not be so this is the minimum type for agent I, where he starts becoming the winner. That means his virtual valuation has started becoming the largest one. That is the way to think about it, even though the formal definition is here. So, you first check whether there exists at least one agent whose virtual valuation is positive. If that is the only agent who has become who has a positive virtual valuation, then he will pay that value W inverse 0. If there are more than one agent, then you will find among them who has the highest virtual valuation, equate that with the second highest virtual valuation and invert that Ti. So, the value of the Ti where this Wi is actually equal to the second highest virtual valuation, that is the point where so that is the value that it should pay. So, in a way this the whole optimal mechanism for multiple agents for selling one single item is that where you allocate the item to the agent who has the highest virtual valuation, assuming that there exists at least one such agent, and the payment is there is a reserve price and it is a second price auction with a reserve price, and the reserve price is that value for that agent, and that value could be different depending on which agent you are looking at, because different people may have different valuation distribution. So, we will take an example to understand what this actually means, and that will clarify some of these ideas. Yeah. Yeah.
How are we sure that this W inverse at 0 is not a set but just a single value?
Because it is regular.
No. So, yeah. So, it is just saying monotone non-decreasing. Right. Yeah. So, it could be a set, but
why can't we just take the supremum? If that
yeah,
is set, we can
just take the supremum. Yeah. Right. Yeah, you are right. I mean, it could be a set because, yeah, but I think you can create. Did we assume non-decreasingness for Wi's? What was the regularity condition? Regularity is yeah. So, weak inequality. So, yeah. So, you can have a set. Yeah, you can just take one of the highest point in that case. Okay. Yeah, I think those are small technicalities. Okay, so let us look at this example to understand what is the revenue optimal mechanism in this case. So, there are two agents, two buyers. They have different set of so 0 and beta i's are different for these two agents. So, first agent will have a value between 0 to 12, 0 to 18 for the other agent. They are all independent, their distributions over these types are independent and they are uniform. So, these are agents both of which have the same type of distribution even though their supports are different. So, you can calculate what is the virtual valuation for agent 1. This is 1 over 12 and 1 minus GT is T1 over 12. Simplify, you will get 2 T1 minus 12, and similarly for agent 2, 2 T2 minus 18. Okay. Now, let us look at each of these cases. I should have actually uncovered this. So, can someone explain why this is unsold in the first row? So, what is the optimal mechanism? Optimal mechanism will first do the allocation, and the allocation rule is right. So, Fi of t was 1 if Wi of Ti is greater than equal to Wj Tj for all j, 0 otherwise. If Wi, I mean this is the else condition, the if condition is written here. So, if Witi is negative for all I, then unsold, right. So, here if you look at these values, so if you plug in 4 value here, the virtual valuation is negative for player 1, and for this value virtual valuation is also negative. So, nobody is going to give me positive expected utility, positive expected revenue, so I will not sell this object. Okay. So, what happens for the second case? Why is it sold to 2? So, for the first agent it is still negative, and for the second agent it is positive. So, how do we calculate the price? Clearly, you cannot compare this and that. So, the way we are going to calculate this is, yeah. So, this is true that the valuation, the virtual valuation is maximum for agent 2, but we will, so the agent 2 will not start becoming the winner until it crosses the 0 value, right. So, even though it beats this one, so we will not be comparing this with this value, because that is a negative value. So, the moment, so here that between this two, that maximization point W I inverse 0 is turning out to be the maximum. So, if this virtual valuation becomes equal to 0, the point where the W is actually taking off and becoming positive, that is the point where agent 2 starts becoming the winner. So, therefore, you equate it to 0, you get the payment, that is the payment for agent 2. Okay, so, for 6 and 6, W2 is negative. So, you look at this one and yeah, so you look at this one and the point at which it becomes exactly equal to 0, that is the payment that you charge. So, which in this case becomes exactly equal to its type. Okay, so, the 9, case. Here both of these are non-negative, right. So, who has the higher virtual valuation? Player 1 has higher virtual valuation 18 minus 12, and this is 0. So, player 1 will win, and he will pay the, I mean you can imagine that this is 0 or yeah. So, you can just equate that equal to 0. I mean this two, you are comparing between these two, agent 1 will start becoming the winner when it beats it, that means at 0, right. So, that is the point where you get 6. Now, 8, 15 both are positive now. How do you find the payment? Or so, okay, so both are positive, but you see that T2 is significantly larger. So, you will so this virtual valuation is larger at T2 equal to 15 than T1 equal to 8. So, between these two agents, this agent has higher virtual valuation. So, I will give the item to this agent, but I will equate. So, where at which point will this agent start becoming the winner? You will have to equate it to the value where T1 is 8 here, right. So, the idea is that W2 T2, let us say I call that point T2 star, that is the point where it starts becoming the winner. This has to be equal to the W1 times T1, which is given by here, right. So, if the other agent's type is T1, which is 8 here, I will have to at least bypass that value in terms of my own virtual valuation, otherwise I will not become the winner. So, this turns out to be 16 minus 12, right. Sorry, yeah. So, 2 times 8, yeah, somebody correct me if I am doing something wrong. So, T2 star minus 18, right, is it correct? So, is 4 and 22, right. Okay. So, T2 star will turn out to be 11. So, that is the payment that this agent should make. That is how we got that number. Okay. So, now the at least how we can use it depending on. So, if you are given different distributions not uniform, you know how to calculate that, you find the corresponding virtual valuation function, do this calculation, equate it, you can even write a program to find the optimal auction. Any questions about this example? This is just the illustration of the optimal auction. Okay, so I think we are almost at the end now. So this is one special case, the other example where all the bidders are, let us say, it should be symmetric bidder, not systematic bidder. So symmetric bidders, that all the valuations are, so the agents are all IID agents. So their type set is the same, the type, the set of types TIs are all same, their distributions are all same for every agent. So then the virtual valuations are also going to be the same, it is the same function. So what happens is that you give the item to the agent who maximizes the virtual valuation, and because of the regularity condition, this happens only when their types are also having the same same monotonicity, right. So your type, if your type is the highest, then your virtual valuation is also the highest because it is the same function. Now the object goes to the highest bidder, that is the meaning of the optimal auction, and it is not sold if this W inverse, again I think this is many typos, I will correct it. So W inverse of 0 is going to be greater than TI. Yeah, if the type is smaller than that value, that T star value, then you will not sell it. So that that point below which, so because it is the same W function for everyone, so the 0, the inverse of the 0 will also be the same point. If for every agent that their types are smaller than that value, then you will not sell it. Yeah, this is the right one. Okay. And that, okay, so that also turns out to be the payment if either you pay that value, which is this reserve price, or you pay the maximum of all these TJs, right. So anybody remembers what this mechanism is? This is directly looking at their types. So you have seen this mechanism before. So you give the item to the agent who has the highest bid value, and you charge him the second highest or this value. So what mechanism is that? Oh, the answer is written here. So the second price, it is a second price auction, right. So it is just the second price auction because you are your payment is the second price, excluding you what is the maximum, and yeah. So and if that happens to be negative, I mean here there is no chance of getting negative. So W inverse 0. So W inverse 0 could be something even larger than the second highest bid, that is still possible. It could be such that your reserve price is like 50 rupees and all the bidders except you were below 50 rupees. In that case, you will charge 50 rupees, not the second highest bid. So second price auction with a reserve price. So this is one special case where if the bidders are all symmetric, they are all IID ones, your optimal mechanism is the second price auction with a reserve price. Now we actually started with an objective of the BIC mechanism, the truthfulness guarantee. We also wanted the individual rationality guarantee. We did not care about the efficiency part, the Pareto efficiency or the allocative efficiency, that was not the objective. Rather, we wanted to have the revenue maximization. So this example is going to show that what is this tension. So we cannot really have both optimality and efficiency. Here is an example where you are achieving optimality according to our rules and it is not efficient. So let us see why. So if you do this calculation, it is a very similar thing. So you have two different agents, agent 1 having valuations between 0 to 10, the other guy is having between 0 to 6, and both are uniform distributions and independent. So you can calculate the W1 T1, W2 T2. So if they are, so you will never sell the item if both of these things are negative, right. So that happens below. So for for T1, if that is below 5, that in this region you will not sell it, and also T2 is less than 3. So within this region you will not sell this item, right. and that is already inefficient, because in the efficiency guarantees that you should maximize the sum of the valuations. So that is anyway there, but we will also show something which is a little more non-trivial. So once you have, so if you look at these two lines, so this T1 2 T1 minus 10 line, which line will this be? Yeah, so this one. So okay, no, so that is not the correct line. So you will have to compare between these two numbers, right. So you will have to compare between whether this virtual valuation is larger than this virtual valuation. So W1 T1 is greater than or equal to W 2 T2 under this region. Let us say we are breaking ties in favor of agent 1 anyway. So then you get a equation of a line. So that is 2 T1 minus 10 is greater than or equal to 2 T2 minus 6. Whatever that equation turns out to be, that is essentially this line when you set it as equality. So when T1 is larger than that, that is you are on this side, then you will sell it to agent 1. If you are on this side, and then you will sell it to agent 2. That is the optimal mechanism according to what we have done so far. And this line is essentially V1 equal to V2 line, right. So this is the case where because I am going to sell it to exactly one agent, the efficiency guarantee is asking that you will have to sell it to the agent who has higher valuation, right, for that object. It is a single indivisible item. The objective is to maximize the sum of the valuations. Some of the valuation will get maximized if I give it to the agent who has a higher value. So if I pick a point here definitely V1 is larger than V2, yet the optimal mechanism is actually giving it to agent 2. And the intuition is that even though you have the real value, the raw value of that agent to be higher, because we have a distribution, our expected revenue earned will be smaller if I give the item to agent 1. So therefore, even though it is maximizing the valuation for agent 1, the virtual valuation is actually less for agent 1, and therefore I am giving it to agent 2. Okay, so this is just showing that these two things are different. You can have a mechanism where you maximize the revenue, but that is actually not giving you the efficient outcome. Any questions? I think we are almost at the end.
Please could you again specify the notion of efficiency and optimality?
So efficiency is sum of the VI. So this is the same as before. So efficiency is allocative efficiency, or Pareto efficiency and allocative efficiency is the same. So we pick, let us say, the valuation of these agents by doing this allocation such that I am using the previous notation, not this notation, because that is the way we have defined it. So you pick the allocation from that allocation set such that the sum of the values are maximized. Now here in this particular case you have this A, which are like A1 up to AN, and each of these AIs can take values 0 or 1, and the sum of these AIs can at most be 1. So you can sell all the give the item to exactly one agent. So if that is the case, then I should give it to the agent who values that item the most. Right? That is the simple thing. You can actually, in this context, you can write it as FIT times your TI, summing over I in N, because this is the probability that you are going to give that item to agent I and then multiply with that TI, and you should definitely give it to the agent who has the highest TI. That is the only way you can maximize this. So that means in this region you should give it to agent 1. That is an efficient allocation. But we have just seen that that is not the case. because the decision boundary for optimal mechanism is further on the right.
So efficiencies for the agents and optimalities for the auctioneer, because he or she wants to increase the payment rate.
So both are objectives of the auctioneer. So auctioneer earlier, in our earlier view, we wanted to maximize this. Let's say we are calling this social welfare. We were trying to maximize the social welfare and not worrying about what the revenue earned. So there we could use VCG, which happens to be the second price auction in this case, and that is not optimal. That second price auction is not optimal here. So here the objective of the auctioneer has changed. Now it's not bothered about whether it is efficiently allocated, that is the painting, even if it does not go to the most valuable agent, I want to maximize the revenue. So this was the thinking that we had, right. So why should the auctioneer even worry about whether the most art loving person gets the item? As long as I gain the maximum amount of revenue out of it, that's my objective, and here is the objective, and that cannot be efficient in that way. Okay, so I think that's the whole thing. So I didn't have anything else to say. Most of the topics that we have discussed related to optimal auction. So you can actually ask a little more involved question where you are doing this single object allocation. So I can give you some of the recent things that we have done in this space. Again, using this idea of Meyerson auction. So the problem of even selling two indivisible objects. So yeah, so let's say I have two objects A and B. So far what we have discussed is I have exactly one item and I know how to optimally sell that item. But when we have two or even more items, the valuation is more complicated, right. So now you have a valuation for A, you might have a valuation for A and B together, or you can have a valuation for B and the empty set is always 0. So we do not know what is the optimal revenue maximizing auction in this case, even after. So this result came in 1981. For more than 40 years we do not know still this answer. So that's one classical thing which we couldn't solve. So people have solved some special cases. So let's say if the valuations are additive, what will be the solution? I mean, I'm giving the easiest possible answer. The valuations are additive. I have two different objects. V of A comma B is just the valuation of A plus valuation of B for the same agent. Then I can run a Meyerson for each of these items separately, right, because the revenue is going to be again additive. This is perfectly separable problem. The valuation that I get from any bundle, I can always break the bundle and treat each of these items as separate. If I maximize the revenue for each of them, I also know that I have maximized the revenue for each of them for the bundle together. So that's a very simple setup. People have looked at submodular valuations, like if you have valuation of any set and if you add one more item to it, so if you add it to a smaller set, then the difference in your the marginal valuation gain is larger in the smaller set than the larger set. Yeah.
In the single item option, the type of emission is the bid value as for the single item that's being auctioned. What about the multi-item auction?
So I'll just treat this as two different auctions. So I'll ask only the agents about their valuations for item A and run an auction as before. Treat the B as a separate item and ask everyone's valuation for that and run. So maybe I may give A and B to the same agent if their virtual valuations are the highest among everybody else, but it may go to different agents as well. Yeah, so was that your question or?
Because you mentioned about it being separable, it was
Oh, so I said separable in the sense that the problem itself is separated into two different optimization problems. So if I want to maximize the revenue, it's like the payment for this is completely a separate problem, and payment for this I can treat as a separate problem, because finally your utility can also be written as the valuation minus the payment for item A, and valuation minus payment for item B, right? And then I can treat two different problems in a separate way. It's no longer true if I have this bundle is different from this one, maybe larger, smaller, I do not know. Okay, so this is one thing. So a recent trend in mechanism design is to pose this kind of revenue maximization or auction problems on a network. Okay, so what is different here? So suppose I have, so here we are assuming that we always can reach to all the n bidders, right? So suppose there is a seller, so in a way the current problem is like a star network where I have all the seller is connected to all the bidders, and they can directly ask what is your bid, give me your bid, and I'll run a, so suppose still the seller is selling one indivisible item. Here also it is selling one indivisible item, but all these individual agents are directly accessible, and therefore we can run a Mersenne auction. Here the problem is that the seller does not know all the bidders, and therefore it does not even it cannot even run a auction like the one that we have done. So it may only know their the immediate neighbors. But so for instance, I still run a, let's say, second price auction, right? So suppose this is 1, 2, 3 and 4. These higher valued bidders, they are behind 2. So suppose the seller decides that, okay, so everybody reports, so propagates this information, and assuming that everybody propagates this information, I still run the second price auction, that is I give the item to this agent and ask him to pay the second highest bid, which is 3, and I keep the entire amount. So remember that now this the agent 2 has one more strategy that is available to it. It may choke this information, right? So you cannot reach, the seller will never be able to reach to 3 and 4 if he does not propagate that information. So currently he is gaining 0 because the entire payment is going there. If he stops the information flow, then he becomes the winner and pays 1, right? So his net utility will be 2 minus 1, which is better than getting 0. So it makes all sense for this agent, any rational agent, to not propagate this information. So in this setup, the types of the agents are not only this Ti, because Ti is the valuation here, it also is the Ri, is the set of neighbors that it has, and it can misreport any of them. So it can misreport Ti, it might misreport Ri. So in that case, how can we actually salvage the mechanism? So the mechanism designer can say, okay, so I give you some commission for forwarding. So you could have gained 1, so out of 3 I give you 1, okay. Still I am going to gain more revenue, because if you stop the information I get a revenue of 1 because this guy was paying 1. But if I give you 1, then you don't have any reason not to forward it. So I get at least 2. So win-win situation for both of them. So this area of research, which started in 2017, so if you are interested, I will tell you the complete reference. So 2017 by Lee and others. So their title of I think the paper title is diffusion auction design. So they call it diffusion auction because it is actually happening in this diffusion manner. So you are giving some clear incentives for people to forward this information, diffusion auction. And they have actually come up with a nice mechanism. So of course that's just one mechanism, and what we did is we actually characterized what is the structure of this truthful mechanism, just like Mersenne. The only difference is that now you will have to also update the definition of what is truthfulness, because earlier you are only talking about TIs, If you have any other Ti prime, then you will not get anything else, any better utility. You will also now have to say that if your true neighbor set is Ri, you should not be reporting anything smaller than Ri. So, you will be actually propagating everything, and under that condition the necessary and sufficient condition like that, so we call it DDSIC, diffusion dominant strategy incentive compatibility. This is equivalent to a very similar Meyerson like condition. So, where the allocation with respect to Ti has to be monotone. So, your Fi Ti and T minus I, of course, because that is the case, and for every Ri R minus I has to be monotone in Ti. That is one requirement. The second is very similar to the payment structure, but there is a third condition which is actually putting some restrictions on those constant term. Remember that in the payment we had this Ti T minus I, and that had this term which was 0. So, now if you also add this Ri and R minus I's, this third condition is actually putting some restriction. You cannot actually set 0 payments for the agents who are actually critical, right. So, you will need to pay a certain amount of money to the agents so that they actually forward this information. So, yeah, so the long story short, your DDSIC has a very similar characterization still with an additional condition. And yeah, so there are various updates to this mechanism which has been trying, I mean we are trying and also other people are trying to do to maximize the revenue at the center, and if you have special type of nodes which does not have Ti. So, suppose there are only relay nodes here, then what happens and so on. So, it is an active area of research. So, this diffusion auction design is an interesting area of research, because now a lot of things are happening on the network. So, this actually comes from a very applied domain, because social networks are being monetized. So, people do want to run the auction, let us say these advertisements, but they want to push that through other agents. So, let us say you are a company who wants to sell a certain object, you want to push, so you want other people to advertise, and if someone is interested in purchasing that item, then you get some revenue, but you also give some commission to the agents who actually brought in that customer. Okay, any questions? I'll stop here. Finished quite early, but that's fine.